Alright, so let's say that we want to find the area under a particular function. So that's going to be any arbitrary function of x. It might be something like this. And we want to specify 2 points along the x-axis between which we want to find the area. So the area would be the area underneath that curve, above the x-axis, and between those two fixed points A and B. So this is an interval that we usually denote as square brackets AB. So that's a closed interval because we're including everything up until those two limits there. So what is the area underneath this curve going to be? You might think, well, that's not a that's not something we can do, right? Because we know the area of simple shapes like a triangle or a square are quite simple, because all you need to do is you need to multiply things together, and you can use some geometry to manipulate expressions around, and you can usually derive expressions for this. So because you know that a triangle, for example, it's just half a rectangle because it's just cutting through the diagonal like that. So you can derive an expression for the area of that using basic geometry. But for a function like this that is always changing and that is quite smooth, how do you find the area of that? Well, this is a question that perplexed mathematicians for quite a long time, especially people who work with calculus. And there is actually a method that we can use to do that. So let's say that we break down this area into little rectangles, because rectangles are essentially the easiest thing that you can think of when it comes to calculating an area. So I'm just going to change the color, and I'm going to draw a few rectangles here. I'm going to draw 4 rectangles like this. So those 4 rectangles, if we add them together, then it should approximate the area. Obviously, they're not going to be exactly the area we want, but they will approximate it up to a certain level of accuracy. So what we're going to do is we're going to take the width and define it as delta x, and the height of each rectangle is simply going to be the value of the function f of x at that point of x where we evaluate it. So we're going to take the initial point, so the point to the left of the rectangle, to be the height of the rectangle. So this is going to be f of x j. So j is just a subscript that refers to which point of x we're taking out of the whole set of points that we're going to create. So we're going to create sort of a grid here. We're going to break it down into little slices, and then each of those points is going to have a value of the function f of x, and then each of those is going to be the height of the rectangle. So delta of x, we essentially want this width to be constant. We want it to be the same for all rectangles, because that will give us a better approximation, a better method for approximating this. So the best thing we can do is, let's say we have n number of strips or rectangles, then obviously we should divide the whole interval, which is b minus a, by n. Because if we have 4 rectangles in this case, then our delta x is going to become b minus a over 4. And that's the easiest thing that we can come up with. So how does this actually compare when we actually make the rectangle smaller and we add more rectangles to the area so that we can approximate better? Well, let's say that the area under that curve is approximated by the sum of j equals to 1, that's a subscript term. The function of j, this is the height of each rectangle, and delta x is going to be the width of each rectangle. So what we're doing with this formula, and that's up to n, so we have n rectangles in total. What this represents is the area of each rectangle. And what's going to happen? What do you think is going to happen as n approaches some number like infinity? Well, if n approaches infinity, then it makes sense that delta x is going to approach 0. That's the only conclusion we can draw from that. But there is another thing that we can do with it. What happens to a number as it approaches 0, but it isn't quite 0? It becomes infinitesimally small. And if you go back to the very first video in this series when we discussed differential calculus and the applications of essentially approximating the gradient between 2 points by using infinitesimals, you will remember that an infinitesimal can usually be represented by dx, so this is just a differential element essentially. So as n goes to infinity, we're going to get close to 0 but not quite, and that's just going to be replaced by dx, and this is something that we use quite a lot in calculus. So if this becomes dx, then it makes sense that this set of points is going to become continuous, because we're going to have an infinite number of those points of f of x running along that interval. So what is going to happen to this? This is actually going to be equal to the integral of f of x dx from a to b, and this is equal to the limit as n goes to infinity of the sum, so this should be equal here, j equals 1 to n fxj delta x. This is how we define what we call a definite integral. A definite integral is an integral in which the final answer you get is actually a numerical value and not a function, as you would if with an indefinite integral, which is what we were dealing with in the previous videos. So this is going to be defined as the limit of n approaches infinity of this sum, because you can imagine as those rectangles become infinitesimally small in width, they're going to approximate the area perfectly, essentially. So this is quite a big this is a very important theorem in calculus, and this thing right here, we call it a Riemann sum. A Riemann sum because this is basically built upon the concept of a Riemann integral, or a Riemann, what they call in real analysis, Riemann integrability. And that's something that is more related to early mathematics, so we're not going to discuss that in here. But what you need to know is that you can actually use integration on a continuous function within an interval that is also continuous to find the area under that function and above the x-axis. So let's solve a few examples just to show you how this works. Let's say we have the following function. Let's say we have 0 to 1 x squared dx. What we need to do is we need to integrate that function on the inside. So x cubed over 3 plus c. So that's the integral of this function. Now what are those limits going to tell us? Well, the limits are going to tell us that we're going to substitute those values into x. So we're going to take the top value and we're going to subtract the lower value. And I'm going to show you why that is the case in a minute. So if we take 1 over 3, so 1 to the power 3 over 3 plus c, minus 0 plus c, then you know that obviously the constants are going to cancel out because they're the same. This is 0, so in the end your area is going to be 1 over 3. So just by performing simple integration, we found the area under that curve, which happens to be a parabola that crosses the origin of the xy plane. So why do we actually subtract the values by putting that value of x into the integral itself? Well, the reason for that is that the integral can actually span the entire area that is covered by that function, and if that function is continuous from minus infinity to positive infinity, then the integral we will be getting is actually the area under that whole function. But because we're only interested in a closed interval, we take the integral from a to b and we subtract b from a, because we are doing it from right to left. So basically we're cutting the area here, so we're ignoring all the area at the right, and then we're subtracting all the area that is to the left, and that leaves us with this closed area here. So that's why we have this expression, and we can generalize this by saying that the integral, or the definite integral from a to b of a function x dx is going to be equal to f of x, which is the primitive function or antiderivative of f of x, a to b. And notice how I am ignoring the constant, because no matter what we do to it, the constant will cancel out as a result of that subtraction. So we're going to end up with fb minus fa. So this is one of the fundamental theorems of calculus, and it allows us to find the area underneath any curve. So you might be wondering, well, what does this tell us about functions that may have an area below the x-axis? Well, that's a good question. When you have an area that goes below the x-axis, the integral will also tell you what that area is. The one thing it won't tell you, though, is that if the function happens to be odd or even, it might happen that you will get a zero area, even though it is technically not zero. So what might be an example of that? Well, let's say we have a cubic function or a cubic polynomial function that is symmetrical. Well, it's anti-symmetrical, but it covers the same area above the x-axis between some point minus a and a. Then when you integrate this area, you're going to get a positive area, because that's what the integral is going to tell you. But when you integrate this area, you're going to get a minus area, and because both areas have the same magnitude, they're going to cancel out in the integral. So the integral will tell you the area between this point and that point is zero, even though it's actually technically the sum of those two areas, and it is graphically it is not zero, but that's the definition of the integral. So for any integral that is from minus a to a, so we're looking at something that is maybe symmetrical about the y-axis, we can have two options. So this is going to be equal to one of two options. The first option is going to be, this is going to be 0 if f of x happens to be odd, and this will be equal to 2 times the integral of 0 to a of f of x dx if f of x is even. So why is that? Well, if you look at an even function like x squared, and you take a point minus a and a point a, you know that an even function is always going to be symmetrical about the y-axis. And what this means is that you're going to, well, not about the y-axis, but about a specific axis. It has symmetry. So what is this going to be equal? Well, this area is going to be equal to that area. So obviously the integral of this is the same as saying 2 times this area or 2 times this area. So that's why we have this definition here. So just to do a little recap of what odd and even means, an odd function is one that does not satisfy the property actually, just to show you that. So let's say we have the function x cubed. What happens if we put, so it shouldn't satisfy. If we put x cubed, if we put minus x into it, minus x cubed equals to minus x cubed. So is this the same as that? Well, it is actually. So this means that our odd function should actually satisfy this property. It should be equal. How about an even function? Well, let's say we have x squared, and if we put a minus x here, that's going to turn out to be x squared. So it is not equal to this. So an even function has the property that f of minus x is different from minus f of x. So that's how we define those two things. And we can show that by integrating things like that. So in general, for an odd function, you will get 0 when you take this, the size of the interval is symmetrical about the y-axis. And that's essentially the idea behind this. Now, the other thing that we need to take into account is that definition of the Riemann sum that we talked about a little bit earlier. So we need to take into consideration the fact that sometimes you may not be able to find an exact integral or the exact area under a curve, because maybe the integral that you're trying to work with, the function that you're trying to integrate, is actually too complex to integrate and it doesn't have an analytic solution. So in such cases we can use the Riemann sum to approximate the area. So just to show you, we're going to use the same example we used before. So through analytical methods we found out that this is equal to 1 over 3. Now let's say we want to use a Riemann sum with 4 terms. So let's say we have the function, and now we're going to have x squared like that. This is going to be 1, 1 and 0. So this is going to be the area we're going to integrate. And now we're going to have 4 rectangles. So we're going to split this into 4 sections. So that's going to be 0.25, 0.5, 0.75. So the first rectangle is going to have the area 0, because remember that we're going to use the endpoint to the left of the rectangle as the height. Now for this one, this is going to have the height of this endpoint, so that's going to be this. For 0.5 we're going to have this height, so that's the third rectangle, and for the last one we're going to have this height. Now you can obviously see, even from the graphical representation of this, that using 4 rectangles is not going to be good enough, and we're going to have a reasonable amount of error in it. So what is this going to turn to be equal? Well, the integral is going to be approximately equal to the sum to 4 terms of j equals to 1 of the function, which is in this case x squared j, times delta x, and delta x is going to be defined as the interval 1 minus 0 over 4, which is 0.25. So that's how we found out that that was the step size in our approximation. So what we're going to do now is we're going to choose 4 points. Remember, we choose the end point to the left, so that means that x1 is going to be 0, x2 is going to be 0.25 because we have moved delta x steps forward, x3 0.5, and x4 equals to 0.75, and this gives us x squared equals to 0, x2 squared equal to 0.0625, x3 squared equals to 0.25, and x4 squared equals to 0.5625. Now what we're going to do is we're going to add all of these results together and multiply them by 0.25, and in the end what we're going to get from this is the answer 7 over 32, which is around 0.21875. So if we want to find the error in this calculation, we just simply subtract this from the original value, which was 1 over 3. So the error in this calculation, or in this approximation, is actually going to be about 0.11458. So how does that compare to the original exact value? Well, if we take the ratio of this error to the original value, that actually accounts for around, so percentage error in the approximation is around 34.4%. That is quite a lot of error into it. So obviously using 4 rectangles was not a good idea at all. If we wanted to do this, we would need to use at least 100 rectangles if we wanted to get something reasonable below 5% error. But that's just to illustrate the idea of how this works and how you would use something like a computer to make a better approximation of this by having a lot more rectangles involved. So obviously the accuracy increases with the number of rectangles that you add to your function, and that's what the whole idea of definite integration and the Riemann sum is all about. And in the next few years we're going to be applying this area under the curve and numerical integration to a few more problems.